Hello and welcome to the session. I'm Dr. Akshay Kumar from School of Computer and Information Sciences, and in this session I'll be discussing with you about maximum bipartite matching. Bipartite matching, what is it? Before we learn bipartite matching, let us try to understand what is a bipartite graph. Now, as the name suggests, bi means two. So, two parts, right? Bipartite. What are we dividing the graph into two? Probably not, right? So, consider an undirected graph G, all right? If it is possible to partition the set of vertices V into two sets, V1 and V2, such that all edges Pi to Vj belongs to E are such that Vi is in set V1 and Vj is in set V2, right? If that is the case, then what all the edges go from sets V1 to V2. So, if all the edges are going from set V1 to set V2, then it is basically you have a bipartite kind of a graph. This is a typical example of bipartite graph where there is V1 set is basically represented by left nodes, all right, and V2 set is being represented by right nodes, and what you can see, all the edges are from V1, all this. There are no edges between V1 set, there are no edges between V2 set at all. Okay, so all the edges are from set V1 to V2. All right, so this is how you see that the bipartite graph is defined. Okay, so is it clear? You can no edges among themselves. There is no edge in this among any vertex of V1 set. Okay, or but from V1 to V2 all the edges are there, okay, and this V2 and these are unidirectional edges, so you can say it is vice versa also, because the solution of this particular matching is from V1 to V2. So, we are going to consider it in a slightly directed way only. Okay. So, this is a bipartite graph which consists of two sets of vertices. L in this particular case represents V1 and R represents V2. Okay, so this with this definition, let's move on to what is maximum bipartite matching problem. Okay, now maximum bipartite matching problem is a matching problem only specific to bipartite graph only, the graph which we discussed right now. Okay, a matching in a bipartite graph consists of a set of edges such that no two edges of the subset of graph share a vertex. So, no sharing of vertex. Okay. So, a matching will be maximum matching, that is maximum number of edges, if adding any edge from the graph makes it no longer a matching. All right. So, let us look into this particular definition. Okay. So, what is the maximum bipartite matching? Okay. So, this was my L set and this is my R set. All right. So, the first matching in this particular case is coming since there is an edge over here. All right. So, there is an edge over here. So, we can take this particular. Okay. Now, we have already added, there is a matching here. So, this matching is this. Okay. Now, the next we have a matching from here to here, okay, or matching from here to here. So, let's say we selected this matching, all right, that is okay. So, we have got another matching. Now, this particular node, okay, there cannot be any matching because if I add that particular thing, then bipartite nature, matching nature is gone. right? Because only in a bipartite matching, what we have said, that no two edges of a subset of graph share a vertex. Okay, so once we start doing this, it is sharing the vertex, it is not allowed. All right. Then comes the next. Okay, so we can have an edge from here to here or an edge from here to here. Okay, suppose we select an edge from here to here, that is also perfectly okay. Then we select an edge from here to here, that is okay. But now this no longer will be required, and we can select an edge from here to here. So there are number of ways by which we can well, possibly we can make this bipartite matching, but what we really need to say that we are getting a maximal, and after that this particular property might be over. So what we really require is a bipartite matching. Now, how to find out this particular bipartite matching? Okay, so what we can, once again, if we have a look, we have a matching between, let's say, if I call node 1 and node, this is 1, 2, 3, 4, 5 and 6, 7, 8, 9, 10 and 11. So, what is matching? 1 to 7. The next is we have 3 to 8, then we have a matching 4 to 10, okay, and a matching from 5 to 9. This is not allowed, this is not allowed, only this is allowed in this particular case. So, we get a maximal bipartite matching in this particular case. All right. So, 1 to 7, 3 to 8, 4 to 10, 5 to 9, this is representing a bipartite matching. Whether it is maximal or not, we have not gone through that, but then if I add any more edges into it, it will destroy the property. Now, where exactly this kind of a thing is used? Okay. Now, let's take many real world problems actually require this bipartite matching. Let's take a very simple example. Suppose we have L applicants, okay, and R jobs, which each applicant having a subset of job interests. So, out of R jobs, okay, so if I say these are L applicants, all right, and these are my R jobs. So, these applicants, this particular, okay, here we say applicants and jobs. Okay, so this particular person may be interested in job that is 7 and job 9. Okay, all right. So, this particular person may be, one is interested in 7 as well as 9, 2 is interested in 8, okay, that is all, 3 is interested in 8, 3 is interested in 9, 3 is interested in 11, 4 is interested in 10, 4 is interested in 11 also, okay, 5 is interested in 9, all right. So, like that, and 6 is interested in only 10, all right. So, like that there are cases applicant and jobs, and what we need to maximize that most of the applicants get job of their interest, all right. So, if we try, that is maximal matching, so we want that most of the people get jobs of their interest. Maybe a particular case when one or two applicant may not get the job, all right, that is all right, but most of the applicants, okay, because in any case here the applicants are more and jobs are a bit less, all right. So, not all are going to get the job in any case, however, in this particular case, right, but the our objective in this particular case is that they should get maximal number of jobs. All right. So, that is what is the application of bipartite matching, and it is a very useful algorithm in many graph based application. All right. Now, how to find the maximum bipartite matching? The algorithm to do so is not very direct. All right. and what it requires is transforming the bipartite graph into a flow network. Flow networks are typically a network of nodes where flow of some information or some weight or something is going on, right? And normally, one very useful algorithm which we will be using in this particular case will be Ford-Fulkerson algorithm. So, we will try to find Ford-Fulkerson algorithm using the bipartite matching using Ford-Fulkerson algorithm. So, what we will do? We will try to identify the maximum flow. All right. So, this maximum flow is the maximum bipartite matching which is possible in the graph. All right. So, this is the way this particular algorithm is going to work. Let us look into the steps. So, the first step then will be construct a flow network, all right, because we are following Ford-Fulkerson algorithm which works on a directed graph. So, we got to create the flow network. All right. So, a flow network, how do we create it? So, a flow network G dash, if we call it, flow network is also a graph. So, right. So, we are referring to flow network graph which is G dash consisting of vertices V dash and E dash, edge set E dash, is defined by adding a source node S and sink node. So, we will be adding two nodes in the set of two bipartite graph. So, suppose our graph was G with the set of vertices V and set of edges E, then in the set of vertices we will add two nodes S and T. So, if I have added in my graph two nodes, okay, how exactly I am going to? It's going to be a directed graph, all right. So, V dash becomes V union S and T, all right. That is very easy to say because set of all the nodes and we have added two nodes in it, S and T. What about edges? Now, from the start node, we will have an edge to each of the left or the V1 set of nodes of the bipartite graph. All right. So, what we have over here on the when U is a member of L, okay, there is an edge from S to U. All right, for every U which is a member of L. So, all the left nodes, left side nodes or V1 part, okay, of the bipartite graph, what we are going to have? There are going to be an edge from the node start or the start node. So, we will create an edge. It was not there earlier. And all the edges which were there earlier, which were part of E, they will be part of this particular graph obviously. Okay. So, all the right side, okay. So, suppose we have just two nodes in the right side and all the edges which were there, okay, all the edges, so this is not there. Okay. So, all these edges which are part of the E, that is edge set of the bipartite graph, they will also be there. And in addition to that, from these nodes, there will be an edge to sink. All right. So, we from every node of R, which is V, okay, there will be a edge, will be an edge to the sink. Okay. So, this is sink, this is the that is the source. Okay. Source and sink. So, we have added. So, somehow we have created the flow network from a bipartite graph. All right. And flow network have edge weights also, because that tells us that this much flow can pass through this particular edge, something like road networks, right. So, obviously, if you have 3 lanes, 4 lanes kind of roads. So, obviously, if you have 4 lane nodes, obviously the flow of traffic from that particular lane is definitely going to be higher. So we need to represent weight. However, when we are using the matching, the capacity of every new edge is marked as 1. So in a bipartite graph, we'll just mark every node to be of capacity 1. And whatever other edge nodes are there in bipartite graph, if they are 1, they will remain 1, otherwise they can change to whatever the node markings were there. All right. So that is how we will do the step 1 when we are constructing a flow network. All right. So if we see, this was our graph. So this is what our L and R is. All right. And it remains unchanged. Okay. So it remains unchanged. It is like that. Okay. Now, if I add, so this is my start node, okay, and these edges, okay, and they will have a weight of 1, and since there is no other weight, so all the nodes will have a weight of 1, okay. So this is the way we can create the, okay, so these are the edges towards this particular thing. So a typical bipartite graph, okay, now what we have created, this is a flow network graph, all right. And now how the next thing which we need to know is apply Ford-Fulkerson algorithm, all right. So find the maximum flow. How do we find the maximum flow? Ford-Fulkerson algorithm is the most efficient method to find a solution for the flow network. It uses breadth first search to pick a path with the minimum number of edges. So we might try to get the or depth first search, whatever we want to do, but if I am using breadth first search, we will try to do maximum number of edges. The Ford-Fulkerson algorithm computes the maximum flow in the network by applying the greedy method. So now first step is going to be breadth first search, which we are not going to do. All right. We can also use depth first search, okay, because from one particular source to one particular thing, we can also use the depth first search. All right. So that is something, okay. And to find the maximum flow, the intuition behind it is, so we can go for DFS also if the need so be, okay. And then the intuition behind it is to keep augmenting flow among a path until there is no augmenting path. So we are not going to go for the search operation, but then how the Ford-Fulkerson algorithm augments different paths and finds the maximum flow for a given situation. Okay. So for that, what we need to define is a very important graph which is called residual network graph. All right. For a graph of flow network say G and a flow in that graph say F. So if we are saying G is the graph, okay, and flow in that graph is say F, a residual network graph say GF defines the uh, uh, edges as the residual capacity of an edge is the computed as. So when we are referring to the residual network graph, we need to define the edges. The nodes are not going to change. The nodes remain the same. What is going to change is the edges. And how we are going to define the edges? The residual capacity of an edge uv is computed as, suppose there is an edge uv, okay, in the graph original graph, our graph G, that is flow network. So if there is an edge uv, then how you are going to compute? You will be computing the capacity of the residual network graph of a particular link uv, okay, or at edge uv as capacity, original capacity of edge uv minus the flow which is going through that particular link. Seems complicated, but let us do an example and you will remember this. Okay. So that is how, that is the capacity minus flow. So suppose a particular road allows let's say 4 lanes, all right, and 2 lanes have been used for specific reason, then obviously the capacity of that particular road is going to be only 2 lanes, aren't we? So this is, isn't it? So this is exactly what we are trying to say here, all right. So these edges can take on more flow because only 2 lanes are being occupied, so other 2 still can take the traffic or the flow. Okay, these edges and if CFUV equals to 0, then UV will not be part of the residual network, because if all the 4 lanes are being used for, let's say, for specific person, for specific traffic condition, then obviously they are not available for the flow. So this edge will not be represented at all in the residual graph. All right. So this is the logic. This is very simple logic. There is nothing much about this particular logic. All right. However, when you are using Fulkerson algorithm, right, for some instances the algorithm may like to decrease the flow of certain edges. So whatever was the flow of certain edges, you would like to decrease it. Now that will be possible if you design a reverse edge. All right. So a reverse edge VU for an edge UV is created in this particular algorithm, okay, and the weight given to that is the amount of flow which is going through that particular edge. That many reverse edge you can create, right? That is how it is. So suppose 2 lanes are being used for the forward traffic. Those 2 lanes, if need so be, can be utilized for the reverse traffic also, and no more forward traffic if some optimization is needed. Now that is being represented by this particular value, all right. That is CFVU, is that is the capacity of a particular residual in the residual node is of a node VU, the reverse, okay, is equal to the amount of flow which is being passing through a particular node U to V. Okay. So this admits flow in the reverse direction. So it's very interesting concept. Let's look into the example, then only you will be understanding it. But before the example, let us look into the Ford-Fulkerson algorithm first. So what Ford-Fulkerson algorithm says, that a graph is there, the start node is there, the source node and the sink node. Okay. So given a network G dash, V dash, E dash with flow capacity C. So there is a flow capacity C, okay, a source node S and a sink node T. Flow capacity C is actually an array, okay, which basically refers to every edge. So there is a capacity with each edge UV. So what does it computes? A flow F from S to T. Our objective is to compute the overall flow from S to T, all right, of maximum value, okay, and FUV is assigned. So initially the flow, that is, we are not using initially any of the capacity. So flow will be 0 for each and every node, all right. So that is what is the initialization. For all edges you will initialize the flow to be 0. Flow of edge UV is going to be 0 initially, while there is a path P from S to T. Okay. So now we will start considering various paths from S to T, okay, which are in the residual graph, such that residual capacity, okay, is greater than 0 for all edges UV which are falling in the path. So you have found out a path which has some residual capacity. Okay. So suppose there is a 4-lane network today initially, then there is a 2-lane network, then there is 1-lane network. So what is going to be the overall capacity? The smallest link, right? That is 1 lane only. Okay. The problem comes, or the traffic snarl comes, because what we are doing, from 4-lane we are directing the traffic to 2-lane, then 2-lane to 1-lane. Obviously there are going to be traffic jams. So what amount of traffic should be allowed from this particular flow path? We should allow only single lane traffic in the entire network in this particular case. All right. So, that is what is basically while there is a path P from S to P, okay, and what you are doing? Find the minimum. That is what I am saying. Okay, find the minimum capacity, flow capacity, okay, of the residual network, okay, or the residual graph. Okay, so minimum will be found out. Minimum will be found out by the edge which has the minimum capacity. So, for each edge then what we will do? Okay, so once we have found out the minimum capacity, we will simply for each h u into p, if the h is part of the h, that is the flow network edge, we will add it into the flow overall flow. So, the flow has increased in that particular edge. Okay. So, that we will be sending flow along that particular path. All right. Otherwise it is the reverse link which we have created. All right. So, we might reduce that particular value in the case of return flow. So, let us see how it works. So, pseudocode first of all, okay, the main idea of the algorithm is to incrementally increase the value of flow in stages where at each stage some amount of flow is pushed along an augmenting path from source to sink. Initially, the flow of each edge is equal to 0, while loop is performed for various paths. The amount of flow from a path equals the maximum flow possible among the edges of the path as indicated by the residual capacity of each edge. That is what we had been discussing. The algorithm terminates when current flow does not accept an augmenting path. So, we keep on augmenting, we keep on finding paths which are augmenting. An augmenting path is a path P from the start vertex to the end vertex T that can receive additional flow without exceeding capacity. So, let us look into the example. Okay. So, this is my start node, this is my node A, B, then C, and this is my T node. Okay. So, how this whole thing, this is, we have not considered L or R sets in this particular case. So, these are the flow which are possible, maximum flow which are allowed through these particular paths. All right. So, this is how it works. So, this is my graph. All right. Now, what happens? So, we start with the path which can take the maximum capacity. So, we find that S to C and C to T, okay, it can take a capacity of 6 here and 8 here. So, what is the minimum of these two values? 6. That means this path can be allowed to carry only a weight of or a capacity of 6 only. So, 6 out of 6 is going to be 6, this is going to be used, all this will be used, and only 6 capacity will be used out of the 8 capacity. Okay. So, 6 of the 8 capacity has been used from C to T. All right. Now, we make the residual graph. Now, residual graph in this particular case is going to be, what was the case for residual graph? These node remains unchanged because nothing has changed in these nodes. All right. So, all these values remains unchanged, but C to T, all right. So, still C to T there is a capacity of 2, all right, and since we are using 6, that is the flow is 6 from this particular thing. So, we create a reverse link of capacity 6. Suppose in the future we might change this particular node, then we can use this particular link. Okay. So, we create in this reverse link from T to C of capacity 6. Still there is a possibility of flow of 2, and another this 6 by 6, okay, this value will be once again used to create a backward link. Okay. So, this is how this residual graph has been done. Let us look into the next step. Okay. So, this was my step. Now, let us look into another path. what is another path in this particular case? So this can maximum take 4, 10, 10, 10, 4. So this is what is going to be my next node, 4 by 10, 4 by 10 and 4 by 4. Okay. And how the residual graph will be? Since only 4 is being going, so it's residual weight for this particular forward movement is 6 lanes are still possible, 6 capacity is still possible in the forward direction. However, in this particular case, all the capacity has been utilized, so only there is a backward link of 4, 4 and 4, because the 4 is the reverse node which we want to create. Alright, so we are able to do this, okay. And as a final step, what we see, there is a capacity of 2 here, there is a capacity of 6 here, there is a capacity of 5 here, there is a capacity here. So still there is a path. Alright. So this third path now will be used. Alright. Now when we use this third path, this overall now has earlier the only 4 lanes were used or 4 capacity was used. Now 2 more will be used, so that we are getting 4 plus 2 as 6, and 2 by 5 will be used here, and all 8 capacity is being used in this particular case, creating a backward link of 8. Here a backward link of will be of capacity 2, and forward link still there is an unused capacity of 3, there is an unused capacity of 4 and a backward link of 6. And here the forward link is 6 and backward link is 4 only, because we have not used any other any more capacity over here, and here the backward link is 4. So now there is no more path. So what is your overall capacity? How much this particular node, if you want to link it, see the total capacity, there is a maximum flow of 12, 8 plus 4, and out of which if you see then path S to C to T is giving you flow of 6, path S to A to B to T is giving you a flow of 4, and path S to A to C and to T is giving you a capacity of 2. So overall you are getting a maximum capacity from this particular graph of 12. Alright. Now how do we use this particular thing in maximum bipartite matching? We find the maximal flow, and with all weights being 1, okay, what you are going to get, this is what the network which you have created, and over here what we are getting, okay. So there is one link over here, okay, then there is another link over here, then we have one link over here and one link over here and another link over here. So what we are getting is 1, 2, 3, 4 and 5, and all are distinct, okay. All are distinct, they are still following the properties of bipartite matching, okay. Why? Because L is connected to this, only one, okay. Similarly, this is connected to this, only one link, okay. This is connected to this, okay. If I number them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and 11, all right. Then what our mapping is 1 to 7, then we have 3 to 8, then we get 4 to 11, then we have 5 to 9 and we have 6 to 10 as our mapping. So now you can see we could find out the maximal flow. The algorithm used is Ford-Fulkerson algorithm, which we had discussed with the different weights, but here weights are going to be only one. So you can easily determine the back flow, you can easily determine the forward flow. Now what is the time complexity of this algorithm? Well, to find a path in residual graph is of order V plus E dash, okay, which is order E, and if we use depth first algorithm, the number of computations for while loop depends on number of times the maximum flow is transformed, okay, because the looping number of loops are very important. So if the number of loops are then we can say the running time of this algorithm is that is the number of times that is the flow network is transformed, that is TF, into number of that is the number of edges, and if the number of flow which are to be transformed are less, then it is order E only. Okay. So, with this, let us summarize what we have done in this particular session, that maximum bipartite matching is a useful way of solving many real life situations, like matching a person to his or her job interest. The maximum bipartite matching problem can be solved as a maximum flow problem, and Ford-Fulkerson algorithm can be used for this particular purpose after converting the graph into a flow network. Okay. With this, we end this particular session. Bye for me.